Variance is what two statisticians are at. And that joke might be a little hard to understand right now because we're about to study variability, which leads us to the value of variance, which leads us to the value of standard deviation, one of the golden rulers for statisticians. And this is actually probably a completely new lesson for you in the sense that you may have never calculated standard deviation. Now, this is a really cool applet that's on GeoGebra that's going to let me explore a more powerful way to measure spread than IQR. So first of all, these are some data points that I have here, and we've taken the average or the mean, and that's 1.4. And the cool thing is, if I move the data point, you can see how this is dragging the mean lower as I pull it further away from the group, right? So basically, if I wanted to look at the spread of the data, one thing I could do is look at all these numbers here. Now, this is E is 4.6 above the mean, D is 2.6, C is 1.6 above the mean. A and B are both below the means, and you can see this should show a negative, but the software is a little picky, and it's showing the negative here. So these are below the means. So these are called the deviations, which is the distance from the point to the mean. I can't really use the total deviation because that's 0. And 0 is not going to tell me a lot about the spread. If I move the point, it's still 0. Even if I bring these over this way, it never changes from 0. So I don't want to use that point. I don't want to use just the deviation. So how could I make this not add up to 0? I could square them. Let's go ahead and take a look at this data set, -4, -2, 3, 4, and 6. What is the mean? Well, we're going to go ahead and do that the simple way, add everything up, divide by how many points there are, and we get 1.4. And that, what we're going to then do is calculate how far is each point from the mean, and we call this the deviation. It's using the formula x being the data point minus x bar being the mean. -4 minus 1.4, and I was just trying to show what I'm subtracting from here. So I'm subtracting the mean from -4, and I get -5.4. So that's actually my deviation right there, not this piece. And now I'll just show you the deviations for the other points. 3 minus 1.4 is 1.6, 2.6. And by the way, you're probably going to notice a pattern that deviations tend to start negative because you tend to be below average if you sort your data in ascending order. And then you get above average and your deviations go positive. If I add all these up, yes, I get 0 again. So they add up to 0. So the way we could get around this is we square it to get rid of the negatives. So basically, for my squared deviation, I'll have x minus x bar squared. So -5.4 squared is 29.16, and 11.56, etc. Now, if I was talking about an entire population, I divide this by n to get the variance. So we're going to divide it because if I have different size sample sets, if I have more points, that means I have more variance, but maybe I really don't. So we always want to make sure we take into account our sample size, and that determines how big this is going to be. So 71.20 divided by 5 is 14.24, 14.2. Then, because this is unitless, I mean, this is squared units, we're going to take the square root to get back to our original units. Now, this is for the population. But most of the times in statistics, we're dealing with samples, not populations. We divide by n minus 1. And there's a technical reason, and I haven't really looked at the derivation of it. But, so 71.20, what changes is the 5 becomes a 4. So I get 17.8. And the square root of 17.8 is 4.22. And it's probably a good thing because that means that our standard deviation for samples, since we don't have the whole population, we don't know as much, is just 4.22. All right. This is also known as the standard deviation, and it might remind you of a little geometry theory we call the Pythagorean theorem. All right, let's go ahead and look at this example where we have the measurements of level phosphate in the blood of a patient. and there are 6 consecutive visits. And we're going to determine the mean and standard deviation. Well, to find the mean, I have to add these all up, and I got 32.4. Go ahead and divide by exactly the number of data points, just like we normally would do. And I get the mean is 5.4. 5 points. Now, these are not in ascending order, so I don't know if I'm going to get positive or negative first. If they were, I know I'd get negative first. So 5.6 minus 5.4 is 0.2. Then we get negative 0.2, negative 0.8, etc. And when I add these all up, I better get 0. Now I'm going to square all of these. Notice you get the same thing from 0.2 and negative 0.2. That makes sense. And add those all up. That's 2.06. So that's the sum of the squared deviations. To get the variance, I'm going to have to divide by n minus 1. Our sample size is 6, so I'm actually going to divide by 5, and I get 0.412. And then to find the standard deviation, I take the square root of that, and I get 0.642. So the standard deviation in the levels of phosphate in the blood are 0.642. Now this brings up the two formulas again. Variance for samples denoted by S squared. And so if you're using a calculator, sample standard deviation is going to have an S on it. And it's the data point minus the mean squared, add them all up, and then divide by n minus 1. For a population, it's sigma squared, so that's a Greek symbol. And it looks, instead of x bar, we use mu. Mu stands for the parameter. And we're going to divide that one by n. Make a note that this symbol, the sigma symbol, means sum of, that we have to add everything up. Now, there are some different ways to look at how big the spread is. One way we can look at it is we can, in case we want to know if it's wider than average or less wide than expected, we compare it to our average. And what we're going to do is we're going to put the spread, which is S for the standard deviation, over the average and then multiply it by 100%. And because I have these two with units on them, this is called the coefficient of variation, does not have units. Now there's another cool thing about spread described by Chevy-Chef's theorem. And he says that for any set of data, it doesn't matter what it looks like, whether it's a pretty bell curve or a uniform distribution, that the following proportion must lie within k standard deviations on either side of the mean. And this is the proportion 1 minus 1 over k squared. So if I go 2 standard deviations from the mean, I go 1 minus 1 over 2 squared, 1 minus 1/4, 3/4, or 75%. So I know that 3/4 of the data is going to fall within 2 standard deviations on either side of the mean. And if you do that for 3, you actually get 8/9 or 88.9%. Now I'm going to show you just a very quick, cool alternative formula for calculating standard deviation, which is easier with spreadsheets. And the derivation is a little tricky, but good news, you're not going to be tested over this, even if you're in AP Stats. All right, so we have this formula for standard deviation, right? But I'm going to go ahead and look at just this top part. So I have it here again. I'll distribute. All right, so I have x squared minus 2x times x bar plus x squared. So that's kind of like a squared plus 2ab plus b squared. Then I'm going to break it up into separate sums. And then I'm going to pull the constant out. X bar should just be a number, all right? And so the 2x bar comes out because that's just a number. The mean squared is just a number. I pull that out and I leave a 1 in. All right. So this is my formula here. Oh, and the thing is, if I have summing up 1 for n in the sample, I get an n right there. Now here's a cool bit. You can remember that x bar is just the sum of x over n. So I can actually substitute that in for x bar here and here. And multiplying all this out, believe it or not, I'm going to get minus 2 sigma sum of x squared over n plus 1 sum of x squared over n, which means that I end up with minus 1. Divide that by the original n minus 1, and I get what's called the computational formula. So why would we want the computational formula? Sometimes it can actually be a little bit easier. So I can revisit that blood phosphate level problem. And here's the data, right? So I only need 2 columns when I use this formula because I need the sum of x squared and I need the sum of x. Well, the sum of x is 32.4. So let's go ahead and square the x's. Notice I don't have to subtract the mean and add those up. Substitute them in, and I get s squared is 0.412, and the standard deviation is 0.64, the same thing we got before. Now, let's go ahead and do the coefficient of variation since we're here. And I do need the mean for that, which, as you may recall, was 5.4. So 0.64 divided by 5.4 times 100% is 0.119, or 11.9%. All right. Now I'm going to try and figure out 3/4 of the data must be within what and what. So they're going to be centered around this mean of 5.4. Well, I'm going to go 2 standard deviations below. So first of all, calculate 2 standard deviations. 2 standard 1.28 below 5.4 is 4.12. 1.28 above 5.4 is 6.68. If I want 8/9 of the data, I'll do 3 standard deviations. So I'll have 1.92 below 5.4 is 3.48, and 1.92 above 5.14 is 5.4 is 7.32.